This is a type of video book. You, the viewer, are encouraged to treat it as any other book. Skip ahead to certain sections, review particularly interesting sections, etc. A table of contents follows, and the current location is always shown at the bottom of the screen. References are detailed in footnotes which appear on the screen while the appropriate information is being discussed. The philosophy for using this medium to communicate scientific information is an embodiment of the phrase, "A picture is worth 1,000 words." It is my belief that a picture with a simultaneous technical explanation is worth even more. The subject matter, low-energy collisions with a surface, is described at the level appropriate for first-year graduate students. This video book may be of use in courses on surface physics, plasma material interactions, or other related topics. It will also be of value for researchers seeking a detailed view of molecular dynamics. I would like to thank the staff of the National Center for Supercomputing Applications at the University of Illinois in Urbana-Champaign for their financial and technical assistance. Individual contributions to this effort are enumerated in the closing credits. Dr. Michael Baskis's video of molecular dynamics collisions of hydrogen on a nickel surface inspired this work, as well as the papers he and his co-workers have produced on the subject. I'd also like to thank Dr. Michael Baskis and Dr. Dennis Manos for their critical review of this material prior to publication. Table of Contents. 1. Molecular dynamics, embedded atom method, and interatom potentials. 2. Video animation, display methodology, potential energies, surface features, velocity vectors, and computational environment. 3. Reflection simulation, incident flight, effects on lattice, and surface relaxation. 4. Absorption simulation, incident flight, comparison to binary collision model, and effects on lattice. 5. Re-entrant flight, incident flight, multiple interactions lead to sputtering, binding energy, and collective surface motion. And 6. Summary and conclusions. A surface of 6 by 6 FCC unit cells, 8 unit cells deep of a nickel lattice, were simulated using molecular dynamics. The method chosen was the embedded atom method, developed by Murray Daw and Mike Baskis. Their molecular dynamics code, DYN52, was used with a time step of 0.5 femtoseconds. 11 different runs of 200 to 1200 time steps each were conducted for this work. On a Cray XMP48, each time step took approximately 8.5 CPU seconds. The positions, energies, and velocities of each of the 1,048 atoms were recorded at each step. Each atom interacted with all other atoms in the simulation, though after the nearest 15 or so neighbors, the interactions were insignificant. 3 of the runs were chosen for visualization. Molecular dynamic calculations are based on numerically integrating Newton's equations of motion for a given interatomic force. The forces are determined from the derivatives of the potential energy. Therefore, to predict the future motion of a collection of particles, one only needs to calculate the potential energy of each atom at every time step. This potential energy will be a sum of the interactions with all other atoms in the simulation. In a metal, there will be an additional major contribution to the energy from the free electrons, which depend on the electron density at that given location in the lattice. The functional forms which describe the electron density in the nickel lattice are taken from fundamental theory. The coefficients for each term, however, are adjusted to fit the experimental data such as nickel's lattice constant, elastic constant, and sublimation energy. The total energy E thus becomes E equals the sum over I of F sub I of N sub I plus 1/2 the sum over I and the sum over J, U sub ij of R sub ij, where F sub I is the embedding energy for atom I, N sub I is the electron density at the site where atom I is placed, and U sub ij is the pair potential between atoms I and J at a distance R sub ij between their centers. This embedded atom method for molecular dynamics in metals has proven effective for a number of applications. As these visualizations will show, molecular dynamics using the embedded atom method is also effective in illuminating many surface effects. Though 6 by 6 by 8 unit cells are simulated by the molecular dynamics code, only the top unit cell, 3 layers of atoms across the entire surface, and the surface features, up to 4 layers of atoms, were visualized for clarity. Each layer of atoms is half a lattice spacing, 1.7 angstroms, apart in the z direction. The nickel lattice continues below the atoms shown on the screen in the negative z direction. Shadows of the atoms are shown on the walls and the floor, allowing the x, y, and z projections to be viewed. The boundary conditions on the simulation are periodic in x and y. To visualize motion across the periodic boundaries, the simulated cell is repeated in the x and y directions. The potential energy of each atom in the lattice is given by its color. All the atoms are bound and have a negative potential energy, ranging from approximately -2 to -4 electron volts. The atoms on the surface, and especially those on the surface feature, are less tightly bound and are colored toward the blue end of the color bar. The surface feature itself is a 4-sided pyramid of atoms, with an additional atom in the center of each of the 4 faces. There is also a small pyramid of only 5 atoms off to the right-hand side. When the simulation space is repeated periodically, the surface features form a series of larger pyramids with smaller pyramids in between. By making each nickel atom into a sphere with the correct radius, the surface contours become more discernible. The surface is reminiscent of a fractal shape over a limited length scale. Amorphous surfaces of a variety of materials have shown atomic scale fractal structures exist. A binary collision fractal model of surfaces has proven useful in predicting experimental reflection and sputtering results. To visualize the path of an incident hydrogen atom more easily, we reduce the visual size of the atoms in the lattice. In addition, the lower layers of atoms are not visualized at all. To show the motions of the lattice atoms, each sphere was given an arrowhead which points in the direction of motion for the atom. The length of the arrow indicated the particle's speed. Initially, the arrows point in random directions due to the inherent thermal energy. These simulations were conducted for a 300 Kelvin surface. The base of the vectors represent the atom's position, while the actual positions of the atoms, and thus the base of the arrows, are moving. Their movement is much too slow to be seen in the timescale of these simulations. The acceleration, and thus the force on each atom, can be seen clearly by watching the change of the velocity vectors. Of the 15 cases cataloged, 3 were chosen for detailed visualization. These cases are described as a reflection, an absorption, and a re-entrant flight. Each case was incident on the same surface. Just the initial X and Y position of the hydrogen atom was changed. A silicon graphics 240 GTX computer was used to render the computer graphic frames using Wavefront and additional software developed at the National Center for Supercomputing Applications at the University of Illinois in Urbana-Champaign. Approximately 5,000 individual frames were rendered for this project. Each frame took between 1 and 15 minutes of CPU time to complete. This first simulation shows a reflection. The 10 eV hydrogen atom is normally incident on the surface, pointing into the pyramid-like surface feature. As the atom passes through the lattice and comes close to a number of nickel atoms, the potential energy of those nickel atoms changes dramatically. The change from blue to yellow represents approximately 2 eV of energy. Of course, for every action caused by the hydrogen atom to the lattice, there is a reaction force on the hydrogen atom. In the visualization, the hydrogen atom's color does not change. The next graph shows the x, y, and z coordinates of the hydrogen atom during the reflection. The background color gives the hydrogen atom's potential energy. The z-coordinate is normal to the surface. Each horizontal grid line on the graph represents 15 angstroms. The vertical grid lines are spaced every 10 femtoseconds. An initial view of this graph seems to indicate 3 primary interactions at roughly 10, 20, and 30 femtoseconds into the flight. The white bars breaking up the color bands at 10 and 20 femtoseconds are merely the grid lines for the graph. Closer inspection shows that each of these interactions is quite complex. This is more easily seen in a graph of the hydrogen atom's velocity components. The units of velocity are angstroms per picosecond, with each grid line representing a change of 400. The 10 eV hydrogen atom has an initial downward negative z velocity of 439 angstroms per picosecond. The first interaction, from 9 to 12 femtoseconds, is actually a rapid series of 2 major interactions with a few minor ones in between. The first interaction slows the hydrogen and knocks it to one side. The second corrects that course and bounces the hydrogen atom downward, leaving all 3 components of the velocity almost unchanged. The effect on the nickel lattice during that collision sequence is seen here. This is the first collision. The shadow on the left wall shows the reaction of the nickel atom most clearly. Here is a second major collision. Again, the wall shadow shows the rapid change of the nickel atom's velocity. The next major events occur between 18 and 23 femtoseconds. These are the hard collisions responsible for the reflection. The hydrogen's z velocity becomes positive. These hard collisions give large kicks to the lattice atoms. This first atom actually interacts twice with the incident hydrogen. Watch how the nickel atom's potential energy fades back and then changes again. The second hard collision has only a single interaction. Now, as the hydrogen proceeds to the surface, it undergoes a non-binary collision here. 2 nickel atoms are affected simultaneously. Only the path of the nickel atom is altered, and virtually no energy is transferred to the lattice atoms. Looking further at its path on this velocity graph, many interactions too small to be visible as potential energy color changes do occur. The most notable are at 38 and 42 femtoseconds. The vector visualization of the lattice does show these interactions. Surface atoms, which have few neighbors, can have significant interactions, even over quite a long distance. The interactions of the hydrogen with the nickel atoms are primarily elastic. the hydrogen atom emerges from the simulation with 8.5 eV of energy. However, due to the large mass difference, little net nickel displacements, or persistence of directed nickel velocities, remain. Even the velocities of the two hardest hit nickel atoms have returned to thermal energies in the 40 femtosecond timescale. There are persistent velocities of the surface atoms which were placed on the faces of the central pyramid. This is due to surface relaxation. The initial placement of the atoms above the first full FCC plane were at standard lattice spacings. These spacings contract due to the absence of neighbors above and to the sides. Though simulations on a fully relaxed surface would have been preferred, the large number of time steps needed to reach the fully relaxed state was prohibitive. In the second simulation, the hydrogen atom penetrates a few atomic layers and then travels horizontally just below the surface for 18 angstroms. At that point, the hydrogen atom turns downward and never resurfaces. Although the visualization stops at this point, the atom still had 6 eV of energy when it left the 30 angstrom deep simulated region. In order to see the types of interactions more clearly, a close-up view of the lattice is used. Note that the initial velocity of the hydrogen is still directed normal to the surface, but this flight will hit just to the side of the surface feature. This particular flight shows that a binary collision code, such as TRIM, may be well suited to modeling low-energy light particles incident on heavy atoms, as long as appropriate choices of binding energies and surface models are used. 5 hard, direction-changing binary collisions occur during the first 95 femtoseconds seen up to this point. There are other atoms affected by the hydrogen motion in non-binary collisions, such as the 2 atoms seen in this frozen frame, but they do not appreciably alter the path or energy of the hydrogen atom. The effect of these 5 hard collisions can clearly be seen by the 5 kinks, 1, 2, 3, 4, 5, in the projection of the atom's motion onto the XY plane. This plot of the x, y, and z coordinates of the hydrogen atom show the potential energy changes of the hydrogen. The 5 hard collisions involve substantial potential energy changes, shown in purple quite clearly. Though there are a number of softer multiple atom collisions, the potential energy change of the hydrogen is much less. A plot of the hydrogen atom's velocity components show the effect even more dramatically. The hard collisions are represented by near vertical changes of velocity. Remember that there are lattice atoms present beneath the ones that were visualized. Their interactions are included in the molecular dynamics code. 2 more hard collisions occur in rapid succession, which drive the particle deep into the lattice. The entire plot of the hydrogen atom's position versus time shows binary collisions occurring on average every 5.8 angstroms. This compares to fractal trim runs of 10 eV hydrogen on nickel, which give an average distance between binary collisions of 2.18 angstroms if the energy of the hydrogen is above 6.7 eV, and 6.54 angstroms for the later part of its flight, where the energy is less than 6.7 eV. Assuming a constant energy loss rate, the overall average distance between collisions is 5.1 angstroms. The entire velocity plot shows the effect of the collisions and their magnitude. 7 hard binary collisions, purple, and 4 softer binary collisions, red, affect the path taken by the hydrogen. The energy of the hydrogen at the end of 200 femtoseconds is only 5% less than its initial energy. This number of interactions are of the same order as in fractal trim calculations, 2.3 interactions per reflected flight and 27 interactions per absorbed flight. The molecular dynamics simulation from Section 2, a reflection, showed 4 major interactions, while this molecular dynamics simulation was not carried out for enough time steps for the hydrogen to come to rest. 30 to 40 interactions would not be unreasonable for a flight which does not make it out of the surface. Now let's examine the effect of these collisions on the nickel atoms in the lattice. Each of the hard collisions dramatically increases the velocity of its collision partner. Here, 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 which cannot be seen well, and here. The velocity of the lattice atoms involved in the multiple atom collisions increases, but not by very much. If the energy exchanges with the lattice were greater due to a higher energy or a closer mass ratio between the incident and target atoms, displacements and even sputtering of target atoms could occur. This simulation vividly shows that the lattice atoms most likely to receive sufficient energy to become displaced or sputter are the ones involved in the mostly binary collisions. It is also instructive to search for secondary events. Does the primary knock-on atom, the one struck in the binary collision, affect its neighbors? That effect does occur, but the time scale necessary for the propagation of forces in the lattice and the motion of the lattice atoms is too large to be seen in this simulation. By the time one lattice atom affects another, the hydrogen atom has made many more collisions and started many other primary knock-on atoms in motion. The overlapping of these interaction regions may account for the low, but non-zero, sputtering of certain materials below the so-called sputtering threshold energy. Such an overlap is one of the features seen in the next simulation. In this last simulation, several ion surface interaction effects are detailed. These include the effects of surface roughness, interference of shock patterns from hard collisions, visual proof of the work function concept, and the mechanism by which particles can quickly come to rest in a solid. This particular flight traversed the boundaries of the simulation 3 times. In the molecular dynamics code, the particle then re-entered the cell from the opposite boundary. In the visualization, the cells are repeated, so the true path of the hydrogen atom is seen, and the potential energies of the lattice atoms are only shown changing in the cell that actually should contain the hydrogen atom. The hydrogen atom is again normally incident, but this time at the side of the central feature. The atom then enters the feature, slides down the opposite edge, makes some very hard collisions, doubles back on itself, and would reflect from the surface. However, the central surface feature's presence extends forces, the derivative of the binding energy, and pulls the hydrogen atom back into the surface, where it undergoes a rapid series of hard collisions and loses 25% of its energy in the last 25 femtoseconds. Notice that some of the atoms at the edges of the simulation disappear and reappear, seemingly at random. The forces exerted by these atoms are always taken into consideration in the dynamic calculation. However, the algorithm which determined which atoms will be visualized at each step sometimes shows the atoms at one boundary and sometimes at the other boundary, depending on the thermal motion of the atom. A closer look shows the path of the hydrogen atom more clearly. A number of rapid collisions take place which guide the hydrogen atom just inside the descending edge of the surface feature. A hard collision is made at the base of the feature, sending the hydrogen atom just under the surface, horizontally, as in the absorption visualization of the previous section. Now the atom hits a lattice atom head-on and reflects nearly 180 degrees. This event sends it directly at a second lattice atom, and the hydrogen's path doubles back on itself. It now interacts once again with the first atom that it struck. This last collision sends the hydrogen atom out of the surface. If no other surface features were present, the particle would have reflected. However, the gentle curve of the hydrogen's path shows that long-range collective forces from the surface atoms affect its motion. This is a visualization of the binding energy of the material. The uppermost atom exerts a notable attractive force on the hydrogen, causing it to follow the contour of the feature back into the bulk of the material. The kink in the hydrogen's path is due to the presence of a surface atom near that location. Obviously, the forces from that atom are included. However, it was visualized at the opposite boundary. At the end of the flight, a large number of lattice atoms interact with the hydrogen in rapid succession. In these last 25 femtoseconds, the originally 10 eV hydrogen atom loses nearly 2.5 eV. This plot of the hydrogen atom's position and potential energy shows the huge number of collisions which occur. The first quiescent period, from 45 to 55 femtoseconds, is the period of nearly horizontal motion just under the first layer before the atom doubles back on itself. The period between 95 and 180 femtoseconds is the hydrogen atom's excursion over the hill and back down the other side. The graph of the hydrogen atom's velocity components show the hard collision at the base of the surface feature, which stopped the downward momentum at 35 femtoseconds. The 180-degree collisions at 65 and 75 femtoseconds are also obvious. During the excursion over the hill, a nearly constant force is exerted on the hydrogen atom. This can be ascertained by the nearly constant slope of the velocity component in the z direction. Finally, the last rapid series of interactions is seen. The effects of this flight on the lattice are remarkable. The atom makes numerous collisions, none which change its velocity markedly. After reaching the bottom of the surface feature, however, a hard collision is made, imparting a large force to the lattice. The horizontal travel is uneventful until a head-on collision is made with an atom that lies on the surface, knocking it upward. Within 10 femtoseconds, a second head-on collision is made. The hydrogen is doubling back, but strikes yet a third atom in a hard collision. This collision sends the hydrogen back towards its first head-on collision partner. The hydrogen atom is now interacting with the same lattice atom for a second time. This type of double interaction with an atom that is on the surface or in a surface feature so it has a lower binding energy could explain how it is possible for hydrogen to sputter a heavier solid, such as nickel, at energies below the so-called sputtering threshold. Such sputtering events are rare. The sputtering coefficient for 10 eV hydrogen on nickel at normal incidence is on the order of 5 times 10 to the minus 4, but it still can occur. Sputtering, even at this low magnitude, has a major impact on such things as the device lifetime and impurity control in fusion energy devices. In this case, the nickel atom did not receive a full second interaction because another lattice atom gets in the way. This new collision is the interaction responsible for sending the hydrogen atom out of the material. Watch the effect of this newly struck lattice atom on the nickel atom, which was initially struck head-on. It pulls that atom back into the surface. This has a ripple effect on the other neighbors as well. An atom which has been relaxing into the surface is shoved back upward. Note that these velocity changes of the lattice atoms are due to their forces on one another. The hydrogen atom is far away and is showing no potential energy change at this time. As the hydrogen rounds the top of the surface feature, the uppermost atom tugs the hydrogen back along the local surface. A reaction force is felt which pulls that top lattice atom upward. The sum of these long-range attractive forces from the surface atoms forms the potential barrier known as the surface binding energy for the material. The binding energy of nickel is 4.46 electron volts. At this point, the hydrogen atom has only 4.0 eV of energy directed perpendicular to the surface, and thus cannot escape. As the atom re-enters the surface, a series of sharp collisions happen. Some of these collisions are multi-body affairs, which dampen the velocity of the hydrogen atom quickly. Here, the hydrogen atom is interacting with two atoms simultaneously. Now a third atom is struck before the interaction with the second is complete. A fourth interaction occurs here. A great deal of energy has now been added to this local region of the lattice. This energy is propagated to lattice neighbors, like the one shown here, not by an interaction with the hydrogen atom, but from nickel atom to nickel atom. Viewing this sequence of events without pausing shows a collective motion of the lattice atoms over a large length scale due to the sudden deposition of energy. 2.5 eV of energy are deposited in 25 femtoseconds. The simulations depicted in this video are intended to give insights into ion surface interactions. When attempting to comprehend what actually takes place in this type of interaction on a surface, most researchers resort to some sort of a mental map, a picture in their minds. While no picture can be completely accurate, the video images provided here use the state-of-the-art tools for both the molecular dynamic physics and the computer graphic visualizations of the data. One of the striking results from this work is the importance and effects of atomic scale surface features. Simulations which do not take surface roughness into account will miss many aspects of reflection and the sputtering that could occur. The re-entrant flight would not have re-entered the surface if the features were not present. The reflected flight barely penetrated the actual lattice structure before bouncing off. The potential sputtering event from restriking the same atom from the same direction could only have been sputtered if its binding energy were lowered enough by being on a surface protrusion. The understanding of ion surface interactions is critical to the success of thermonuclear fusion and the growth of semiconductor plasma processing. It is my hope that this publication will foster more understanding and thereby help lead to continued success in those fields. Thank you very much.